thank you all for coming. Good morning. My name is Richter. The dissertation is titled Predicting Melanoma Risk from Electronic Health Records with Machine Learning. So first off, I just want to say thank you to Dr. Khoshgoftaar. Thank you very much to my committee and to all of you sitting here. Everyone here has contributed in some way, so thank you very much for that. We have already gone over this, so 16 publications, 3 of them are still under review on the submission, but so what we're going to talk about today is my dissertation, right? So we'll start off a little bit with some background and some theory, and then go into a couple case studies, more focusing on kind of the application side, on the healthcare application, and then we'll dive into transition a little more towards more machine learning techniques and ways that we can improve the performance of those models. And then we'll finally conclude with some future work. So a little bit of background. This will just kind of lay the framework for like why is this research important, why is it even being done, and then we'll go into the actual methods later. So first up is melanoma. So melanoma, if you're not familiar, is a type of skin cancer. And skin cancer itself is one of the most common cancers, but melanoma is the most dangerous form of skin cancer. So it's expected around this year, around 100,000 cases of melanoma will be diagnosed, and the most important part about melanoma is catching the disease early. So if you can detect the melanoma early, you can usually treat it through an excision, and usually the survival rate, if you catch it early, is over 90%. The problem and the issue is if the cancer spreads to other sites. So in this case, if it spreads to distant sites, the 5-year survival rate drops down to less than 20%. And that results in just over 7,000 estimated deaths through this year. And another interesting fact about melanoma, it's actually one of the most common forms of cancer for younger people, so people who may not actually be thinking about their risk for cancer. So what we look at here is mainly how can we identify high-risk patients so we can track them, be able to detect the cancer early. And we do that using electronic health records. So an electronic health record is exactly what it sounds like. It's an electronic version of a patient's data. So when people refer to EHRs or EHR systems, generally they mean the actual software system or product that's capturing the actual records. And so there's a bunch of different ones. And the benefits to this is actually increased usage, first of all. So 10 years ago, the HITECH Act was passed, which introduces a lot of government regulations around using electronic health records and electronic data transfer. So that's one benefit that's used a lot and actually has the promise of improving efficiency and then improving the quality of care because you have all the patient's data available. So some challenges specifically when you're trying to build risk models from electronic health record data is that because there's so many different systems, all the data is fragmented. Data is not shared a lot of the times. And then a lot of the times too, it's basically just a piece of paper on the computer where the notes are dictated or free text. So we take the melanoma problem, we're using electronic health record data, and then we're going to build risk models using machine learning techniques. I'm not going to go into each one of these points, but these are all the different points that we're going to consider throughout this dissertation. First of all is, can we even build the risk model? And then how can we actually build effective models in the presence of certain properties of the data, such as class and balance? And then what are some ways, more from an infrastructure and tooling perspective, that we can actually process this data efficiently and build lots of different machine learning models. So we'll go into all these in the respective sections. The main contributions of my work here are listed. First off is actually creating a de-identified data set for research, particularly in this dissertation. And we'll go into exactly what the data set looks like and how it was made. Then the first case study is a smaller case study using known melanoma patients predicting sentinel lymph node metastasis. We'll also go into that. The main contribution of this work is the melanoma risk model that actually uses routinely collected office visits to predict individual patients' risk of developing the disease, and we build like an explainable interpretable model that can do that. And then some advanced machine learning methods are used to obviously improve the performance of those classifiers. And then finally, we look at how much data do you actually need to get a performant model. So throughout the research, we found that there's actually some sampling that you can do to reduce the size of the data. So the question is, how much data do you actually need? And we're going to look at that through learning curve approximation and actually use a few different data sets beyond just the one that's presented in this research. So how do we do that, right? So this is how we're going to go into the theory, and then we'll dive into the case study. So I don't have time to go into all the different algorithms. The dissertation actually goes into these more. But from a high-level perspective, what we're doing is supervised classification, where the labels of the data are known. And we're going to be performing classification, basically high risk or low risk. So it's a binary classification task using these machine learning techniques. So these linear model, decision trees, ensemble of decision trees, such as random forest, and boost, support vector machines, and multinomial. So some of the machine learning techniques around the actual classifier, so you can throw a classifier at the data and then it can produce a model. But these techniques actually help to improve the performance, and we're going to explore these some. So the first is feature selection, which is a dimensionality reduction technique that can actually select the most informative features for use in the models. And we do that here with chi-squared feature selection, which is a physical test that tests the independence between two features. In this case, an independent feature and the class label. If they're independent, then the feature is probably not very important. The other technique we use is random undersampling, which combats the problem of class imbalance. So in our case, when we're doing high risk versus low risk classification, this is a toy example of a particular data set. So let's say we have 100 instances in the data, 10 of them are in the class of interest, so positive, high risk patients, and then 90 are in the negative class or the majority class. So classifier will tend to focus on the majority class because there's more samples there, and it's going to try to learn from that, but then it probably overfits the DAC. What you really care about is those positive samples. So what random undersampling does is it randomly removes some of the majority instances to then balance the data set a little bit further. We also try different ratios. This is to create a perfectly balanced set, but in this case, we do a 25% positive class distribution, in which case you can actually still retain more of the negative instances because potentially those are useful also to the classifier, so maybe you don't want to throw away all the data. So we'll look at a few different ratios for that in some of the works. Experimental design. So the metrics that you use for measuring machine learning classifiers is very important because if we use the first measure, the most intuitive one of accuracy, saying how many instances did you classify correctly, in our previous case, if you just classify all 100 of those as negative, you'll still get a 90% accuracy. You're not catching the case that you really care about, which is that positive class, the high-risk patient. So we look at different metrics, all based on this confusion matrix presented right here. Particularly, we look at true positive rate or sensitivity or true negative rate. So if we classified everything as negative, the true positive rate would be 0%. We also look, when all these machine learning models actually produce a probability of class membership. So a number between 0 and 1 that says what's the probability. But if you need to say like a yes or no class label, you then have to determine at what point in that probability does the prediction become positive. So you can say at 0.5, anything over 0.5 becomes a positive prediction. So these metrics are all dependent on that threshold. So you actually have to select that very carefully. There are a couple metrics that are dependent, are threshold agnostic, which means in this case, the area under the ROC curve, it plots the true positive rate or sensitivity versus the true negative rate. And it'll plot that actually upon a number of thresholds. And then if you take the area under that curve, then you get like one succinct measure that can tell you how well your model is performing across all different thresholds. So we use ASC a lot throughout this, and then we also look at true positive rate. The experimental design for how most of the experiments are conducted is displayed here. We do a train and test set, so that way we can have a holdout set to evaluate how well our classifiers are doing. We also perform cross-validation. So in this case, it's 5-fold cross-validation. What happens is you take your data set, you split it up into 5 chunks. You take one chunk, leave that as a holdout set, and then you use 4 of those chunks together as a training set, evaluate it on the holdout, and then you repeat that actually 4 more times with each individual set as the new validation fold. And then you average those, and that's how you can produce a few different runs. So that way you get 5 runs with 5-fold cross-validation. We repeat that 5 times, so that way we can reduce the variability and randomness of splitting the data. And will give us at least 25 runs every time, which allows us to do statistical tests, such as ANOVA for testing the difference between factors, and then Taghi's HSD test, which tells you actually the differences in the differences of the means in the different levels are. And then we do some t-tests for kind of ad hoc comparisons. So I don't have a lot of time to go into the data engineering. There is more in the dissertation that goes into this, but this is something that's really important because it's the only way that we can actually process the data because of the large volume of data in the PHI. So the first off, we do everything in the cloud with Amazon Web Services, and that just enables like really fast scaling of clusters and launching a bunch of different machines when needed. So back when I started my research, Hadoop was kind of like the de facto big data processing engine, but Spark was coming around and actually became really the best processing engine for big data. So we used Hadoop clusters mostly just for the storage and the distributed system, but then Spark is used as the in-memory processing engine that will process all of the big data. So use Spark with the Python API to do all the data processing and inclusion criteria, creating the features. And then once that data set is small enough after all the inclusion, we actually use single machines rather than clusters to do the machine learning. So Spark does have a machine learning library, but we found actually that it was better to use different packages such as scikit-learn right here. So the software used throughout all the dissertation is primarily Python or R. Python is used for all of the big data processing with Spark. It's used for all the machine learning experimentation using scikit-learn and a few of these other packages that are listed here. I actually ended up building an open source framework that allows you to launch EC2 instances with Amazon, execute a machine learning experiment, and save the results to S3, and that way it kind of happens seamlessly. Then you can run that all in different environments. So that's open source on GitHub. And then all of the data analysis, statistical analysis, all of the visualizations and such was all performed with Spark. So the data. I'm not going to spend too much time here, but we'll go through it. So I wouldn't be a good academic if I didn't actually produce something with an acronym. So we produced the MAMEL data set, which stands for Modernizing Analytics for Melanoma, which is the data set used for all of my research here. The key points of the data set is there's over 20 million de-identified patient records in it, and of those, over 500,000 have a confirmed diagnosis of melanoma. So to the best of my knowledge, through the literature review, this is the largest de-identified data set of real-world melanoma patients. As well as the number of patients, there's a lot of depth in the data. So after we do encoding of all the data, there's over 100,000 different data elements throughout this data set. And I'll show you all 100,000 in this distribution. So all this is possible because of Modernizing Medicine's dermatology product, from which a de-identified data set was generated, and I was able to do this research. So I didn't do any of these things, but it's very helpful because I actually got to do the research with it. So the 3 points and what really makes this possible is the fact that first, it's a mobile-first structured data input solution, so you don't have the same problems of free text dictation that you get from some other EHRs. Next, it's on the cloud, which means you have a consistent experience for every single practice, which means all the data collected is all consistent. Other EHRs potentially may have customizations for different hospitals or practices, which makes it hard to put the data together for research. And then, of course, is the large amount of data that can be used for research projects. So I'm just going to show you a quick demo of the product because it's not an advertisement, but it's because it's the easiest way to see what kind of different data is captured throughout this. So this is a patient's chart. You can see some of their past conditions, and then we're going to dive into a particular visit and coming in. We're going to take some history and see why the patient is coming. The patient's about coming in, they're saying they have a skin lesion that they're concerned about. We can go into the body atlas and select the body location there, select some information about the particular lesion that the patient is saying. They might be saying that it's bleeding, but it's mild in severity, and then we'll save that. Right. Next, the doctor comes in to perform the exam, and then they'll perform an exam, full skin exam. We'll see all of the different data elements that are recorded there that can be recorded about the exam. And then the doctor's going to come in and say this is neoplasmosis behavior and going to perform a biopsy. So perform a biopsy on the same location that the patient presented for, and again, you can record a bunch of different structured data. So you can see how the number of data points in this data set balloons because there's so much. So we'll save the visit note, and then I'm just going to show you a summary. So that's just a quick high-level overview of what happens in a patient encounter, and this is mostly where the data comes from. So from a high level to the data elements that are captured from that system are patient demographics, some history, like allergies, things like that. And then the key is in the patient encounter where all that data comes from. So all the findings and diagnoses and prescriptions, treatments, and outcomes that were captured are all collected in the data set. The first study here, like I mentioned, is a risk model to predict sentinel lymph node metastasis. And if you're not sure what that is, I'll tell you. But first off, I need to brag about it. So the contribution to this work is showing that the tumor death is actually very correlated with the risk of sentinel lymph node metastasis. We provide a risk model that actually can give guidance for thinner tumors that may be missed. To the best of our knowledge, is the largest sentinel lymph node metastasis study ever done. A little bit of background here. So when a patient gets diagnosed with melanoma, there's a lesion on the skin that's identified as the tumor. The sentinel lymph node is a lymph node in the body that's closest to that tumor. There's ways to identify that. You can perform a biopsy of the sentinel lymph node, determine if the cancer has spread through the lymphatic system to that sentinel lymph node. And approximately 17% of melanoma patients have a lymph node metastasis. And currently, the clinical guidelines is really if the tumor is thicker than 1 millimeter, you're generally always going to perform the sentinel lymph node biopsy. But if it's less, you only perform it if certain risk factors are present. So the machine learning model that we produce here basically takes historical data about people who had a sentinel lymph node biopsy and uses that to classify people as low or high risk based on the patterns in the data. So for tumors that are thicker than 1 millimeter, you're always pretty much going to do a biopsy. So the machine learning model isn't that important. What it can do is show potentially patients that are low risk may skip the biopsy. But the key is that those thin melanomas that are seen potentially as low risk, if there's other factors there, and we consider they're high risk, then they'll go ahead and get the biopsy. So the population used here, it's around 5,000 patients in the data set. Because of, it's smaller than the original data because we have to only include data where there is a sentinel lymph node biopsy result reported and there's a tumor thickness reported. So because of the clinical guidelines of less than 1 millimeter or greater than 1 millimeter, they split the data set up into a few different data sets. So you can see overall around 10% of patients in our data set have a positive sentinel lymph node biopsy. But then for the thin group, it's around 3% and the thick group is around 18%. But in the data, it's around a half and half split. Around half the patients have a thin tumor, around half the patients have a thick tumor. We really care about that 3% of patients because they might be walking around thinking that they're fine, but they may be high risk for metastasis. So the first thing that we do before we go into all this machine learning on the left here, the first thing that we did was we were talking to some researchers who had actually looked at building a risk model before, and they said they mostly just estimate the risk using the thickness of the tumor. So looking at the data, we can create this rudimentary formula, just basically is the thickness is your probability of metastasis. If it's 2 millimeters, it's a 20% risk. So looking at that and actually plotting the probabilities of metastasis for different groups of patients, you can see that the thickness itself is very highly correlated. It's just one single variable that's telling you how what a patient's risk of metastasis. But again, what we care about mostly for the machine learning is those thinner cases. So to do that, we train a few different classifiers using the experimental design that I presented in the theory section. And these are our results. So the first thing that you notice over here on the right with this AUC column is that for pretty much all the machine learning models, it's not better than the benchmark. So our benchmark we call BT here for progressive thickness, the name of the measure. The machine learning models actually don't do better than the one single variable. And these models have over 2,000 features in them, which is very interesting that this is like a really, really strong biological indicator. But the key things to consider is right here. For the thin melanomas, the sensitivity for true positive, if you just use that benchmark and say, if they're 1 millimeter, biopsy, if they're less, don't, you're not going to catch any of those people who are less than 1 millimeter. These machine learning models, particularly the random forest model, can get a nearly 80% true positive rate, which means you're catching all those patients with thin tumors who actually do have a risk of metastasis. Then on the other side, not as important, but on the other side, for the thick ones, we can actually find people who definitively are low risk, in which case, potentially they can skip the biopsy. I don't know if anybody will actually do that, but they can. That's a quick run through the very first case study. I want to focus most of the time here on the next one for predicting actual melanoma risk. This is taking patients who don't have melanoma, looking in the future and seeing if they're going to develop this. The contributions here is this, based on our literature review, is actually the largest cancer risk modeling study from real-world data. And then the first to actually automatically use data from the EHR to produce this model for melanoma. And that's a key point because a lot of the studies will just take features that are determined important by experts or from univariate statistical analysis. But in this case, we actually throw all of the features there and let the algorithms tell us which features are important. We did a little bit of literature review here and basically found just over 20 studies that produced cancer risk models. None of them were actually for melanoma, but they averaged around 300,000 population size, and they all use less than 100 features. Some of them just use 10 or 20. There was one study that used like 1,000, I think, but most of them just use a small number of features, partially because of data availability, partially because they've only used expert features, and then partially because of the way they did the feature selection. So most of the time they did some univariate analysis method with the survival analysis. I did find actually a different literature review that actually reviewed melanoma risk models. And so these risk models didn't come up in my previous review because these are a little bit different. Those actual risk models were taking healthy patients and then predicting into the future, are they going to develop something? These studies are more case control studies that take a known group of healthy patients and then a known group of melanoma patients, and then they compare risk factors between them. So you can produce a risk model from that, but it's not actually like predicting in the future. So these were all mostly for identifying risk factors. So the total across all studies, they identified over 100 risk factors. And the authors of the survey actually plotted this ROC curve, and they found that all the studies fit along an ROC curve with an area of around 0.75. And spoiler alert, our model does around 0.8 AUC, so a little bit better than these. The population here is going to be a lot larger than the last study that we saw. The main thing here is we have around 4 million patients, 10,000 of whom develop melanoma. And the way we determined that is we found an index visit, which is basically the point at which we make the prediction. So we're going to use the data all up until the index visit to make the prediction for the future. The way we determine the labels is for the positive cases that people who do develop melanoma, you got to make sure that they developed it within 6 to 12 months after the index visit. And for the negative cases, healthy patients who don't develop melanoma, you have to make sure that it's at least 12 months out because you can confirm that they did not get melanoma within 12 months. So what this particular model does is predict risk of melanoma within 1 year. And we can see in the melanoma class that there's a higher proportion of males in the melanoma class, higher proportion of white race, and then a higher proportion of family history. And it's super imbalanced, right? There's only 10,000 out of 4 million are in the positive class. So the way that we do the data processing from the EHR, this itself is a lot of work to do, all the data engineering, collecting all the data together. We process all the data with Spark, like I said. So this is just an example of taking some of those clinical variables out of the electronic health record. We flatten it out into vectors of data for every patient. So we take their index visit and we actually aggregate that separately from the historical visit. So we can try to detect some signals that are maybe different about their history versus their current presentation and their prescriptions and all that. Because of the fact that we have 10 million patients and we have 100,000 features after this count and coding of the data, it produces a very sparse matrix. It means most of those entries in that 10 million by 100,000 matrix are actually zero because patients are seen for certain conditions. So they only have a group of variables just for acne, or a group of variables for skin cancer, and so on. It actually produces less than 1% of those entries in that matrix are non-zero. So we store it in a sparse matrix to make that way more efficient. So what a sparse matrix does is it stores, rather than every single number, it'll store the index of the variable, and then it'll store the value. So that way you're not storing a bunch of different. We perform a count encoding, which basically goes through all the historical data and says how many times did we see this data point. A one-hot encoding would just have a 0 or 1, let's say for acne, but if the patient came in 4 times for acne, the way we do it now is there's going to be a number 4 there. So you can at least capture a little bit more data about some of those longitudinal information. Machine learning, this is the exact same picture that I showed you before. We do cross-validation. The classifiers that we're using is logistic regression, random forest, and XGBoost, using some feature selection for the logistic regression model, and then trying different ratios of random understanding to try to improve the performance of the classifier. These are results here. If you look at the graph on the right, the first thing you'll notice is the x-axis here is the size of the data set, which decreases as you increase the ratio of random undersampling because you're throwing away majority instances. First thing that you notice is the XGBoost model kind of does the best right here at the top. And the main thing I wanted to show you out of all these numbers is that this AUC right here, XGBoost model, if you round up the hundreds, it's 0.8. But you go to the 71. And so, okay, great, right? We did all this data processing, we produced this machine learning model, and we can produce a pretty good model that can predict high or low risk for melanoma. What do you do with that now? Just spitting out a number saying you have a 0.6 probability isn't really all that you should do, especially in a machine learning context. You need to be able to explain why that prediction was made. So I'm going to jump back and actually dive into a little bit more theory right now. But interpretability is really like a hot topic in machine learning research right now because we get more and more complex models that can get more accurate, but you have no idea what they're doing and why they're making that prediction. So there's 2 types of interpretability, and I hope I'm not talking the screen. There's global and local. So global basically says across all samples in your data set, this is how the features contribute toward a prediction. So that's good for risk modeling studies that need to find general risk factors. The other one is local interpretability. And that's what we care about, particularly in this application, is because we want to be able to show why one specific prediction is made. This is the whole point of like personalized medicine and personalized predictions is, can you explain why we're telling this person is going to be high risk? So that way the doctor can look at that data, the patient can look at the data, and then they can see what the model is doing. So the key, this table here shows you just some different types of models and the global or local interpretability they can give. But what we want again is local interpretability, and we do that using the tree ensemble methods of Richter and XGBoost through tree decomposition and SHAP values. And I'll explain what those are. But I just want to start off a little bit with some global interpretability just to kind of get a feet wet. The main thing that you see here is when you have a globally interpretable model, you want to have the minimum number of features because a human can't really understand how 1,000 features all interact in a regression model. So you want a small number of features, but when we produce a linear logistic regression model with only 10 features, it actually gets a really poor AUC 0.6. If we use 1,000 features, then we can get a good model, but now there's 1,000 features to deal with. What do you do there? And this only explains generally across all patients how does the model perform. So what we can see though is that the EHR data is still actually picking up on important signals that are known risk factors. So this ICD code here is a diagnosis code about a neoplasm of uncertain behavior, which means the patient coming in for an unknown skin lesion. And that's a high risk factor because these weights are positive. These negative weights here, we can see that some negative weights are for African American race and a diagnosis of acne, which are kind of known that acne may indicate a younger patient, and the African American race has a lower risk of melanoma. So we can at least see from this that the EHR has the right data and the model's picking up on the right signals. What we really care about is how can we personalize these predictions. And that's where local interpretability comes in. So the first method we look at is tree decomposition using the tree interpreter Python package. And what this does is instead of across all samples, it takes one sample and then it produces essentially a regression model which shows you the different features and the contributions of each of those features. So these are two examples. The top table here is for a positive class, the bottom is for a negative class. We can just see the top 5 features that actually contribute towards that one specific prediction. This is really important because these features are not the same features that I just showed you on the other model. These features are just for this particular patient. So the doctor and the patient can sit down and say, this is why you're high risk because you have a previous skin cancer. Or for the bottom case, you're low risk because you're still younger patients. So you can now do this for every single patient and show them individual predictions. The other method for local interpretability is actually a new kind of exciting field of research called SHAP values. This has probably only come out in maybe the last year. It was presented at NIPS, I think, in 2018, maybe 2017. But what this does is actually takes a technique from game theory and it produces a matrix of every instance and features and the individual feature contribution for all of those instances. So you can actually do a mix of global and local interpretability here. If you average across the instances, you can get global. If you look at the individual ones, you can get local interpretability. So this plot here shows you each individual dot is a prediction. And then the red, the hotter color means a higher value of that feature. And then the x-axis shows you the actual contribution of that feature. The first thing that we see is that as year of birth decreases, the risk, or as the year of birth increases, the risk goes down because it's a younger patients. But the key that I wanted to show through this graph is that you can see actually local groups of data, right? So here, there's some blue, and then there's some red here, but then some more blue here. This one, there's a clump of mixed stuff. So what this shows you is that all features don't contribute equally to all patients. One feature may increase a risk for a certain patient, and that same feature may decrease the risk for a certain patient. So that really shows why it's important to have local interpretability considerations like this tree decomposition and SHAP. One more slide. So just to wrap up this section a little bit, some of the things that we addressed through this research, finding some gaps in the previous work, is first of all, the structured clinical data. And again, I didn't do anything for that, but we can actually use data that's structured. All the other studies had limited amounts of data, so we have a lot of structure. Also, old data, a lot of those studies were actually publishing 5-10 years after the data collection ended. In this work, we published the same year that data was collected. So then that enables for like rapid research and you're actually capturing on consistent clinical practices. And then we use advanced machine learning techniques, right, like XGBoost, the interpretability considerations and so forth. The limitation of this study is that it's still from a dermatology population because this EHR system is for a dermatology product. So you're not really catching patients at the very front line. They're already coming to a dermatologist for something. But found in the data that around 27% of the patients in the data set, their very first presentation was not for any sort of skin lesion check. It was for something like acne or rash. So it still may produce some effectiveness for those people who aren't even really thinking about their skin cancer risk. They're just coming in for some other conditions. We flag them as high risk and then enroll them in the screening program. Now we're going to still look at the machine learning, the melanoma risk problem. But we're going to focus now more on some of the machine learning techniques. This first case is scenarios of limited positive samples. So basically that problem of class imbalance, when you have less and less of the positive samples that you care about, but you have an abundant number of them. The first thing we show that we evaluate classifier performance at different levels of positive samples and show really that a lot of the negative samples are not needed, and we're going to kind of explore why that's the case. So the methodology here is it's the same melanoma risk problem. It's a slightly relaxed inclusion criteria, which allows us to have 9.5 million patients in the data. So rather than that specific like 6 to 12 months or 12 months, we just say, did they have melanoma in 2017? And that's going to be the yes or no class label. That just makes the data set a little bit bigger for this particular case study. And to simulate, so that then produces around 17,000 positive cases. And to simulate even worse scenarios of class imbalance, we'll create derived data sets that remove some of those positive samples. So we'll say, okay, what happens with 5,000 positive samples? What happens with 1,000? What happens with 200? And then on those data sets, we perform random undersampling to see, okay, how does the relationship between this technique that's supposed to alleviate class imbalance and the actual class imbalance in the data sets. So the main thing I want to point out is this table here shows you the negative samples that you get for all these different scenarios. So for the data set with just 100 positive samples, if you fully balance the classes, your data set that you're producing for the model only has 200 instances, 100 positive, 100 negative, when the original data had 9.5 million. So just keep that in mind as we look at some of these results. The methodology here, the experimental design is very similar. The only difference you can see in this picture is the first step where we create the derived data sets. When we do that, we repeat that 5 times. So remove positive samples, do that 5 times, then do the 5-fold cross-validation. That'll give us the 25 different runs. Use a few more classifiers. So we're going to add naive Bayes, SVM, and decision trees here, and then do the whole study. One thing to note too is that because of the cross-validation and the repeats, producing over 10,000 different machine learning models, and if you were to do that sequentially on a single CPU core, it would take you 53 days. So use the power of multi-threading and the cloud, so it obviously did not take 53 days to do this. The results here are looking at, without using any random undersampling right now, we just want to see how do these data sets perform when there's less and less positive samples. So each of these boxes represents an individual HSD test performed for each classifier, and the color shows you the groups of the test. So essentially, 2 things of the same color, they're not statistically different from each other. The first thing that you notice for almost all classifiers, the original data set and the data set with 5,000 positive samples perform statistically the same. And we can see that AUC still gets around a 0.8 AUC. And that's interesting because there is a severe class imbalance. So if you tell somebody, oh, my data set only has 0.18% positive samples, they're going to think, wow, that's super imbalanced. You're not going to be able to produce a good model. But in this case, XGBoost can still produce a good model because there's still a lot of positive samples available. There's still 17,000. So we're suggesting here that the percentage is not always the best measure of class imbalance. It's really the number of positive samples that you have. That's what we're really exploring in this study. This is the results when you apply the random undersampling. The 100 positive sample data set's not shown just for brevity because it was found to be the same as the 200. But the main thing that you see from this graph here, and the x-axis shows you the different levels of random undersampling, so the increasing balance as the x-axis increases. For the data sets with more positive samples, the random undersampling doesn't help as much. So as your imbalance increases, your the effect of random undersampling also increases, which kind of makes sense. And then one thing we show here is that these 3 different ratios of 0.25, 0.35, and 0.5 all perform the best. So in the future statistical tests, I'm just going to show the differences between these ratios and then no random ones. So this is really the main part of the study. This is where we provide a contribution here. This table is showing you the HSD test of the different data sets with or without random undersampling across all classifiers. And the main thing to see here is that a data set without random undersampling either performs the same or worse than a smaller data set with random undersampling. So to illustrate, the original data set without sampling gets the same, statistically the same group as the 1,000 data set with sampling. And the key, and why that's important, is because the original data set has 9.5 million instances, but when you have 1,000 positive samples and then you do a 50-50 random undersampling, you only have 2,000 instances in the data set. So 2,000 gets the same performance as 9.5 million. Also, the most extreme case of this is the random forest with 50-50 sampling on the 200 positive sample data set. That particular data set only has 400 instances, but it actually performs statistically better than the full data set with random forest, which has 9.5 million instances. So really what we see here is that the number of positive instances actually controls the model performance, not so much the negative. You can still have a lot of negative, it doesn't do much. And you can throw out a lot of the negative samples, which means intuitively that they're probably very similar, and the classifier doesn't really need all of those because it can give you enough signal with just a smaller amount of data. We actually explored that hypothesis, and the idea there is that the negative samples are all kind of similar to each other, whereas the positive ones are different. So we look at that using k-means clustering, which is an unsupervised technique. We look at it differently separately with the negative samples versus the positive samples. And then we'll do k-means clustering, I think repeated that like 25 times. So what we do with the clustering is you can measure the distance between each sample and its cluster center and average that across all the samples. And that gives you a measure of how similar are those instances. Because if they're all closer to the cluster center, that means they're all similar to each other. We can see here on this graph that the blue is a positive. So for every different sample of data that I produce and ran the k-means clustering for, the distances between each sample and their cluster center was larger for the positive class. That means the negative class is more similar to each other. So if they're similar, you only need a few of them for the model to pick up information. But if they're different, in the case of the positive class, you need more and more to increase the model performance. That's how we can this is how we kind of prove that. So because of that, the idea there was like, okay, you don't need as much data to produce an effective model. And then obviously that naturally leads to the question of, well, how much data do you really need? How can we determine how much data we need? And that's what this experiment is looking at with the melanoma data and actually a few different other data sets as well. So the contributions here is we performed sample size determination using learning curve approximation on 4 different biomedical big data sets. And there's 2 methods that we use, which is a inverse parallel method that was introduced previously, and then introducing a new semi-supervised curve creation method, which I'll go into. So a little bit of background just on this is that there's this new research area of learning from limited labels. And what that means is because of this era of big data, we're collecting more and more data all the time, right? So you have an enormous amount of data, but if you need to train a classifier, you need to do supervised learning, which means you have a class level, you know what your output is. If you collect a bunch of data, a lot of the times it takes expensive human annotation to actually label that data. So for an example, in like a self-driving car scenario, you have a bunch of pictures and videos of stuff, but humans have to go in and say, okay, this is a stop sign, this is a crosswalk, this is a lane. So that can be very expensive. You can capture images all day long, but it takes a long time to label the data. So one of the questions with that is, well, how much data do I need to label? And that's where these techniques come in to help you approximate, well, okay, this is how much data you need to achieve a certain classification performance. So the way that we do this is using a learning curve. The learning curve is a fairly simple idea, is you produce a model with an increasing amount of data, and then you plot the performance as the data increases, and it gives you a curve such as this. And it usually kind of fits this kind of inverse parallel method where there's a short part of rapid increase, and then it kind of plateaus a little bit. What you care about is that point of plateau, right? It's like right around here, when we're adding more data, it doesn't really give you that much more performance. And at that point, we know, okay, we can stop labeling data right here. And because of the fact that it's a scenario of limited labeled data, you still have a bunch of unlabeled data. So, I was thinking like, okay, well, can we at least maybe use this unlabeled data to help us produce a more accurate prediction for the learning? So the data sets that we use here are 4 different biomedical big data sets. One of them is the melanoma problem that I just introduced before. And the first one is ECBDL, which is a protein contact map prediction data set that was used for several big data competitions. The Medicare one is actually a data set from Medicare claims data to predict fraud, and that was put together and collected through a team of researchers in our group. And then the splice data set is a DNA splice site detection data set. And they're all very imbalanced, they're all very large. The dissertation explains a little bit more of the background on each of these, but I don't have too much time. So the methodology here is we first of all just create learning curves, because in these scenarios we have all the labels, but we're simulating the scenario of limited labels. So first you just create the learning curves with the data, and we basically for that graph, we put 100 points on that graph. And so you basically split up your data set to 100 points. That's what this table is showing you. All the different data sets have different numbers of samples. So on the graphs, I'm just going to show it with the number of positive samples because they're so imbalanced, which would make the total samples, the numbers really big, right? So in the parentheses, it shows you the full data. But I'm just going to show the positive samples just for brevity. But for classification, we'll do logistic regression, and then it's going to do 10 repeats of 5-4 cross-validation just to smooth out the curves. Once we have the actual curves, these are the two methods that are used to approximate those curves. So first is the inverse parallel method, which was introduced by previous work, like I said here. And they even provided their R code, so it's really easy to just take it and try to use it. So what you do here is you actually just use a small amount of data to fit this mathematical model, which is this function right here. And then you solve it for A, B, and C there with weighted least squares optimization. So you're using a small amount of data, so basically it's just up to 100 positive samples, which with the biggest data set would be around maybe 30,000 samples. And then you just get a few points on that graph, and then this method will actually fit the full curve to that small amount of data. So you really only need a tiny amount of data to try and fit the curve. The semi-supervised method actually, what that does, and that's the new one that I introduced here, is you take that same small amount of data, just 100, and you train a classifier on that small amount of data. Classifier is not very good because you don't have enough data to make a good one. But what you can do is then pseudo-label your unlabeled data. So we throw out the real labels of the unlabeled data for this experiment, then we use that classifier from the small data to create fake labels on the unlabeled data. So now you have pseudo-labeled supervised classification, in which case you can then use the regular learning curve method, which is just training a bunch of models on all the different ones. And that actually becomes very computationally intensive, and this study was the largest by far, producing over 100,000 models. And if you sat around running it on one core, you'd be waiting for over 2 years. But have the cloud and multi-threading, so it did only take a few weeks. So the first up, these are the actual curves. So I shortened some of them because there's not much to see when the data gets too big. The first thing that you notice is for the ACBDL, where's the line? Well, the reason that you don't see much of it is because that point of rapid increase actually happens before the very first step. So that means our step size is too big. So in the next, for the following experiments, we're going to shorten, zoom in the step size a little bit. But then what you see here is this vertical dotted line shows you the point at which the model achieves an AUC within 1% of the full data set. So I ran it on the full data set and then compared and found, okay, well, for the melanoma and splice, around halfway through the data, you're getting a model that's within 1%. So like, what's the point of using this data? You're just wasting time and resources. Medicare, we see that probably the model is just not really picking up on a lot with the additional data, because that's actually our most imbalanced data set. There's other techniques that need to happen to help improve the performance of that. These are the results for the approximation methods. On the top here, we see the inverse parallel method, and then the bottom is the semi-supervised method. And like I said, we zoomed in the curves a little bit, so for validation, we only went from 0 up into that point of 1%, rather than going all the way to the full data, because again, you just be wasting computation. The first thing to notice is that the inverse parallel does really well. So if you look at ECBDL and Medicare, just using 100 positive samples, you can predict the performance of like thousands and thousands, potentially millions of samples. It's really good. The melanoma one doesn't do very well, and in the dissertation, there are some tweaks that we can make to the sampling schedule that can actually fit that curve a little bit closer, but I don't have the time to go into that right now. And then the semi-supervised method, we can see that generally it's a little overly optimistic about the AUC, which makes sense because you're creating pseudo-labels and then you're fitting models to those pseudo-labels, which are wrong. But it's a semi-supervised method, so that's why we do that. One thing that we can see actually though with the splice data is while the values, the absolute value of those is a little bit high, a little bit optimistic, the curve actually has a closer shape to the original validation curve, which is the dotted line, than the inverse parallel method. So really what you care about in these scenarios is that point of convergence. And all you care about to find convergence is the shape, right? Because you're just looking for like right around here where the curve starts to plateau. So then you can just use that as, okay, we're going to do this many samples to label, and you're going to go forward and whatever performance you get is what you get, because that's your data. So the dissertation goes into a little bit more on that as well. But we're almost done, so thank you all for here. I don't think anybody fell asleep yet. So this is just kind of going to wrap up all the different things that we talked about. First up was presenting the MAMEL dataset, which is a large de-identified dataset used for the melanoma risk research presented. And the future work here is really like there should be more of these, right? More EHRs should produce more of these datasets from real-world data. We should be studying more diseases because these can actually provide a lot of value to patients to produce all these different risk models. The next is presented the sentinel lymph metastasis risk model, found that the thickness was very correlated with risk, and then produced a model that can show for the smaller, thinner tumors a good model that can tell you what patients' risks are. The future work here is kind of course, you want to try to improve the performance of the model if you can with more techniques, and then potentially deploying this into some sort of clinical setting with EHR. The melanoma risk model was the largest study and the main contribution of this work. Using routinely collected dermatology office data, we're able to produce classifiers that can, first of all, have an accurate prediction, but then also have an explainable prediction for patients and providers. I think a really good avenue of future work for this is doing deep learning with the data, because if you think about that big, large feature matrix, there's a lot of features that have all these relationships that maybe some of these other models aren't picking up on. So I think deep learning models can really have a good impact. As well as potentially combining this with images of skin lesions. So if you can get the patient's history and you can get the picture of the lesion, I think the models can get really, really good. Next is we kind of shifted a little bit more on the machine learning side and looked at the scenario of limited positive samples. Found that the number of positive samples really control the performance of the models, and then not many negative samples are needed. The future work is still kind of like, okay, well, how can you pick which samples are most informative? We know that we can randomly throw them out, but how can you know which ones are gonna be the most informative? And that's kind of related to the field of action. The learning curve with limited labels is we show this sample size determination technique using 4 large data sets and 2 different techniques, one which is an existing inverse power law method, and then the semi-supervised method that I introduced. This work itself could probably be an entire dissertation on its own, because you can try different mathematical techniques, try different other data sets, other classifiers, potentially even like a hybrid method between the mathematical curve fitting and the semi-supervised method. And then lastly is just do more things, right? We can do more data sets, produce more models, and this research really can serve as a reference framework for future studies of like, okay, how do we process EHR data? How do we produce risk models? What tools are good for machine learning? And that's really a big contribution of this work. So with that, thank you very much, and I'll take some questions.